13, 12, 13. Sounds good. All right, so we got into acids and bases last time, and we talked about a couple of definitions of acids and bases, but really an acid is something that has the ability to produce H plus ions, or really H3O plus ions in solution. So an acid is really anything that will sort of produce H plus or H3O plus. And these are free ions in solution, kind of floating around. Bases, on the other hand, are guys that will produce hydroxide in solution, also freely sort of floating around. A more sort of generic definition of acid base, the one we use a lot sort of in chemistry, is the Bronsted-Lowry definition. And the Bronsted-Lowry definition of an acid is a proton donor. So somebody that will give away not just the H, but it is also the H plus. And a base is something that will accept an H plus. The sort of consequence of the Bronsted-Lowry definition of an acid and base is it does sort of create partners on opposite sides of the arrow when we're dealing with that. So we do have an acid and base on the reactant side, and they do have their partners on the other side, which are known as the conjugate acid and the conjugate base. And the acid on one side, its partner on the other side is the conjugate base, while the base partner on the other side is the conjugate acid. Remember that really the only thing that is the difference between those two things is 1H plus. So that can be really the only difference that you should have. And that's because what's really happening here is our acid is sending that H plus over to the base. So the acid will end up, its acid and its conjugate base will have one less H plus than it started with because it gave it away, while the conjugate acid will have one more H plus because that is what it gained. I think that's actually where we left off. Any questions on that stuff there? Yeah. Okay. So we did look at some examples of writing sort of conjugate acids or conjugate bases, depending on what you're given. And as I talked about, sometimes it's important to think about where it came from. So if you're asked for the conjugate acid, that means what you're looking at is a base, and the definition of base, again, should be something that will accept the H plus. If you're asked for the conjugate base, then what you're looking at is an acid, which means it should donate it. So if you kind of think backwards, sometimes that could be helpful. So let's try one here. Let's do HCO3 minus, and let's do the conjugate acid. Let's also do the conjugate base. So starting with bicarbonate there, in each case, right, what the conjugate acid would be are the conjugate base. So take a moment there, see what you come up with. All right, let's take a look. So again, as we talked about last time, really the thing you should know is it's all about the H plus. And the key is to know, should you put it on or should you take it off? So we'll start here on the conjugate acid side. So if we're looking for the conjugate acid on the reactant side, its partner would be a base. So the definition of a base is it should accept the H plus. So its partner there would be H2CO3, a low carbonic acid. If we look to the conjugate base in this situation, the conjugate base partner is really the acid, and the definition of an acid is somebody that will donate the H plus, which means in this case we actually should take the H plus off. And if we take off the H plus, we end up with CO3. And again, something that people sometimes will screw up on is actually the plus part of it. So when you lose a positive charge, you then become one more negative, right? Because H plus is a proton, so you lose a proton, you got like an extra electron. So you end up at CO3 2 minus. So it's really important when you write the formulas for the conjugate acid or conjugate base that you do not neglect the charge, and that's also how we got to 0 over here. +1 and -1, I will zeroed out the charge on that particular one. So it's important, and it's not just the H, but the plus does affect the overall sort of formula, and you do want to take that into account. Now, in this particular case, this guy has the ability to act as an acid or a base. And there are a lot of things that can sort of do that, can act as an acid or a base. A lot of things very much like bicarbonate, which has an H, and it has like a negative charge because it has the H, it can give it away. And it could also accept it because it has that sort of negative charge as well. Those things that can act as an acid or base, those are what are referred to as being amphoteric substances. Water, for example, is an example of an amphoteric substance. Can act as an acid. It can also act as a base. We saw one the other day when we talked about sulfuric acid. That guy, that HSO4 minus. In certain cases, it can accept an H plus and may H2SO4. Other cases, it could continue to lose an H plus and make sulfate. So a lot of guys that kind of look like that, have a hydrogen and negative charge, have that ability to go both ways. We'll talk about later on how you could maybe determine which way it will go, but they are what are referred to as amphoteric substances. Question on Brunstad-Lowry acid and bases. All right, then let us continue on. Speaking of water, which, as I just mentioned, can act as an acid and base, water can even really react with itself. One case, one of the waters is an acid, and the other case, the other water is a base. And that's what we see here. So in this particular case, this guy's going to come and basically grab off that H plus, and that will make H3O plus and OH minus. This is an equilibrium setup here, and we can write an equilibrium constant expression for this. This again would be our product over our reactant, but once again here, that is a liquid, so we will not include it in there. And this expression actually has a special name, as we'll see on the next slide. This is what is known as Kw. I'm going to go out on a limb and go W is for water. So it's the equilibrium constant there for water. And it actually has a value, and that value is 1 times 10 to the minus 14. It actually equals. Now, sometimes you will see Kw written, as we also talked about last time, as H3O plus and OH minus. And again, as we talked about, H3O plus and H plus are really used interchangeable. And again, personally, I will use probably H plus most of the time. But again, anywhere I throw down an H plus, you could kind of slap in an H3O plus, and it's all kind of the same deal. So in this case, we still have our conjugate acid-base pairs, water acid and our conjugate base. Again, the only difference there is 1 H plus, our base water, and our conjugate acid. Once again, only 1 H plus difference between those two. This is pretty much what is going inside water all the time, or really water-based solutions all the time. And as we'll talk about, that's how we know, whether or not it's sort of an acidic solution or a basic solution or neutral. It's how much of the H plus or OH minus is basically floating around in that solution. That's why maybe if you take some water and you test like the pH of it, it's actually acidic most of the time. And that's because it picks up some CO2 from the air and makes some carbonic acid and increases the H plus concentration. Yeah. Nothing really, other than they're floating around in there, and that's what's going to happen now. Well, remember, at some point, it's going to reach an equilibrium, which is going to lock everybody into place. And there's so many water molecules, if you will. There's a lot of water molecules that once it reaches equilibrium, there's still a majority of it being basically a liquid. The only difference is, you have those guys in aqueous ions. So you basically have the liquid part of it, but you still have these guys floating around as aqueous ions. The water molecules that are still intact are basically held together by sharing of electrons. So you have intact water molecules running around. The other thing that we talked about is these are equilibrium expressions, right? Our reactions, and basically those arrows heading in both directions indicate kind of like a weak electrolyte, which means, it's mainly staying together, but it will produce a little bit of those ions and stuff like that. Other questions? So as I mentioned before, we could write an equilibrium expression for this, which is Kw, and Kw is important. We could use it in a calculation. Basically, the H plus part of it, the concentration of the H plus is really the acid part of the solution. The OH minus is the base part of the solution. And depending on the concentration of those free ions that you have floating around in solution will help you determine whether or not basically you will have an acidic solution, a basic solution, or a neutral solution. If you calculate the H plus concentration and it actually equals the OH minus concentration, by the way, at that point, they both will equal 1 times 10 to the minus 7 molar at that particular point. You will have a neutral solution. If you do the calculation and you find that the H plus concentration is actually larger than the OH minus concentration, that basically means the acid part of the solution is larger than the base part of the solution. It will be an acidic solution. And if the opposite is true and the OH minus concentration is larger than the H plus concentration, then you obviously have more base kind of floating around in there, and it will be a basic solution. The concentration of H plus and OH minus in a solution, they run opposites of each other. So what that means is as the H plus concentration goes up, the OH minus concentration heads in the opposite direction. So as you increase the H plus concentration, the OH minus concentration gets lower, and vice versa. As the H plus concentration goes down, the OH minus concentration will go up. So there's sort of a opposite relationship. One goes up, one comes down. And again, I will say that as we talked about, right, the one thing that will affect an equilibrium constant value is what thing affects the actual value of the equilibrium constant? It is temperature is the only thing that will affect it. So it's pretty much this number all the time, but you should still be aware that it is an equilibrium constant value. And as I might have mentioned before, it really doesn't matter what the little letter says next to the K. KW, KC, KP, KA, KB. They're all equilibrium constants, which means they're all affected by temperature. So if you need to use KW, 1 times 10 to the minus 14 is pretty much the number that you use. If you happen to come across a problem, and sometimes books like to do this and go, hey, we're not doing it at 25 degrees Celsius, but we're doing it at some other temperature. You would technically be using probably a different value for KW. They probably would also give it to you somewhere in the problem or something like that. But in just a regular problem or anything, if you're not given any information like that, it is safe to assume that's probably 25 degrees Celsius, and 1 times 10 to the minus 14 is the number that you should use in pretty much all cases. But occasionally books like to kind of throw some of those problems in where they kind of change the temperature. Any questions on that? So we could use this, really, it's the same calculation. The good news is pretty much H plus concentration would equal 1 times 10 to the minus 14 divided by the OH minus concentration. Or if you wanted the OH minus concentration, once again, it's the same calculation, 1 times 10 to the minus 14 divided by the H plus concentration. Really super important. I use the word super there. It's super important to make sure you use your exponent buttons when you're doing these calculations. If you're not using your exponent buttons, you still are not quite sure how to use it. Again, I would highly recommend you come find me and we make sure you know how to do that, because you will be in some big trouble through this chapter here. There's lots of numbers and scientific notation. You want to make sure that you properly put it into your calculator that way. Any questions on that there? All right, so let's give it a go here. What is the OH minus concentration in a HCl solution who has a hydrogen ion concentration of 1.3 molar? So give it a go, see what you come up with. All right, let's take a look. So good news on these calculations, pretty much the same calculation. So Kw here would equal our H plus concentration times our OH minus concentration, and that would equal our 1 times 10 to the minus 14. In this particular case, it gave us the H plus concentration, which is the hydrogen ion concentration, or again, it could be referred to as the hydronium ion as well. That means that the OH minus concentration would equal 1 times 10 to the minus 14 divided by the H plus concentration. Popping our numbers in here, we're going to get that. And put it into our calculator, we do end up hopefully with 7.7 times 10 to the minus 15. This does need some units of molarity like the original guy there, since it is a concentration. Any questions on that one there? So once again, just a friendly reminder, that is 1, your exponent button, your negative button, your 14, and then obviously divide by 1.3 and hit equals. Yeah, that would be the proper way to punch that in. Now, what we want to do at this point is, since we have the H plus concentration, which is the acid part of the solution, and we have the OH minus concentration, which is the base part of the solution, we actually want to compare those two. So H plus concentration versus OH minus concentration. Which one is larger here? So we're comparing this concentration to this one. Which one's larger? It is the H plus, right? 1.3 would be larger. So since the H plus concentration is larger, that means that we would expect this obviously to be acidic, which is good because this is a hydrochloric acid solution. And that would probably be bad if it was basic. So that makes sense. Yeah. Question on that there. All right, let's try another one here. Water particular temperature, the H plus concentration, 1.2 times 10 to the minus 6. What is the OH minus, and is it acidic, basic, or neutral? One of those should be the right answer, I hope. All right, let's take a look. So once again here, Kw is what we want to use. So we got our H plus, our OH minus, equaling our 1 times 10 to the minus 14. Once again here, we're going to solve for OH minus. And again, regardless of which one you're solving for, pretty much the same deal, 1 times 10 to the minus 14. And in this case, we're going to divide it by our H plus, which is 1.2 times 10 to the minus 6. Again, making sure that we put everything into our calculator correctly here, using our exponent button, we will get 8.3 times 10 to the minus 9. Again, we will have some molar. You have most people's calculators, you would have like 8 zeros. And an 8 at the end because you ran out of space. So this probably get to day 3. If you put in scientific notation, that's how you get to the 8.3 part of it. In this case, that eliminates these two for sure. So at this point, what we want to look at is the concentration of H plus, which is our 1.2 times 10 to the minus 6, versus our concentration of OH minus, and which one is larger in this case. It is the H plus concentration. Also a reminder that when you have a negative exponent, the smaller negative exponent is the larger number, because the guy means, like I just kind of wrote up there, you're going 8 places to the left. This guy here, you're only going 6 places to the left with zeros, which makes it a larger number. So again, that's a very common mistake people make as well. So that looks like maybe 4 is a winner there, I think. Question on that calculation there. Once again, if you find yourself kind of getting the right answer but just slightly off, then it is probably how you're punching into your calculator. And you want to make sure you kind of take care of that, hopefully. Let's talk a little bit about pH and the pH scale. So the pH scale runs from 0 to 7 to 14. Less than 7 is acidic. Above 7 there to 14 is basic. And really, dead on 7 is neutral. Just so we're clear, technically speaking, that means you have equal concentrations of everybody at that point, and it is going to give you a pH of 7, and that is neutral. So there's no misunderstanding. That is what we're going to call neutral for us here in lecture is dead on 7. If it's not dead on 7, then it's slightly basic or slightly acidic. So we don't have the gray area of, where does it start and stop? That's what we're going to do. 7 is sort of your central number. As you head towards 0, you become more acidic. As you head towards 14, you do become more basic. And to calculate the pH is equal to, as it says there, minus the log of the H plus concentration. Once again, you can, if you would like, use the H3O plus. It is the same deal. It's basically the acid part of the solution that you put in there. Speaking of calculators, if you have a display calculator, you punch it in exactly the way it's written. You hit the negative button, not the subtract button. You hit the log button, and then you probably punch in your concentration using your exponent button. If you have a non-display calculator, this one and all the rest that we're going to talk about in this chapter probably, you need to go backwards. You need to put the number in first, then hit log, and then hit the negative number. If you're not sure what type of calculator you have, hit the log button. If it says log, then you have a display calculator. Congratulations. If you hit log and it says error, congratulations, you have a non-display calculator. So whichever way you want to go there. So display calculators, where you hit log and it says log, you just punch it in exactly the way it's written. Non-display calculators, you always got to kind of work backwards as you punch it into your calculator. So neutral here is when we just talked about the concentrations of the H plus and OH minus equal each other. And that is going to give us an H plus concentration of 1 times 10 to the minus 7, which will give us a pH of 7. If it's acidic, again, we will have a pH of less than 7. And if it's basic, we have more OH minus, so we will have a value that is greater than 7. The relationship here is as the pH goes up, the H plus concentration goes down, and vice versa. The more H plus you have, the lower the pH will be. So the more free H plus. By the way, again, what we're talking about here is basically free floating H plus in the solution, not attached to anything, just kind of floating around. And again, the levels of that are the levels of the OH minus that's doing the same thing, floating around in the solution, is really what affects, obviously, the pH of the solution. Any questions on that there? So let's talk a little bit, though, about sig figs and pH, because everybody likes that. So when you calculate something like pH, your answer should have the same number of decimal places as the concentration value has significant figures. So when you calculate something like a pH from the concentration value, when you're done with your pH value, you should have the same number of decimal places as the concentration value had for significant figures, and vice versa. If you start with the pH type value and you calculate the concentration, however many decimal places there are is how many significant figures concentration have. So let's try one here and make sure our calculator works. If we got the H plus concentration, 1 times 10 to the minus 5 molar, what is the pH? Times 10 to the minus 5. And again, if you have a display calculator, that's negative log, and then enter the concentration correctly. Non-display, start with the concentration, then hit log, and then hit negative. Regardless of that, you should get the lucky number of 5 staring at you, hopefully, on your calculator. Yeah. So what should we record? 5, 5.0, 5.00, 5.0000. So what we want to look at here is the concentration value, and the concentration value here, this number, has how many significant figures? It does have 2, which are those as well. So the concentration value has 2 significant figures, which means the pH value actually will have 2 decimal places, not significant figures. So we're going from significant figures to decimal places when we calculate something like pH, and vice versa. If we're going opposite and we have 2 decimal places, then we would end up with 2 significant figures on there. So it is sig figs at decimal places. This should be the correct way to report it. Definitely not that one. By the way, this would be acidic, basic, or neutral. This one would be, it would be acidic. The pH is less than 5. You should 100% of the time always look at the pH value to help you decide if it's acidic, basic, or neutral, because the pH scale is what everybody has in their head and not something like the pOH scale, which we'll talk about here in a second. Any questions on that there? So there is the pH scale here on the left. And again, some of the things that you might be familiar with, that's a strong base. So it's definitely basic. Strong acid, which is obviously very acidic. Here are some other acids. Pure water is 7. But again, as we talked about, you know, if you have your water sitting out for a while, you might be in that range there as it picks up the H plus from the ground. Another useful way to calculate something is on the pOH calculation. The pOH is equal to minus the log of the OH minus concentration. So if you're given perhaps the OH minus concentration, you could actually calculate the pOH. The nice thing about that is there is a nice relationship of, if you take the pH plus the pOH, it will equal 14. So this allows you to perhaps shortcut some calculations. You might not have to use kW, knowing again that the pH is minus the log of the H plus, and our kW that we've been using here, our H plus, our OH minus, equals 1 times 10 to the minus 14. So there is actually a variety of ways that you could solve the same problem depending on sort of which pathway you choose. They all should really give you the same answer once said and done, as long as you didn't screw up too much on the calculation. But the pOH scale actually runs opposite of the pH scale. So on the pOH scale, you still have 0, 7, and 14. Below 7 is actually basic. Above 7 is acidic. So it runs opposite of the pH scale. So if you have a low pH, you will have a higher pOH, and vice versa. If you have a high pH, you will have a low pOH. So this is why I said a second ago that you should really look at the pH value, because that is usually the scale most people have in their head. Most people don't really have the pOH scale in their head usually. So you should definitely look at the pH to determine, probably in most cases, is it acidic, basic, or neutral. By the way, when you're asked that question about a solution, is it acidic, basic, or neutral? How many answers should there be? There should be 1. But I have gotten many different answers on that question. And the reason is you calculate the pH and go, cool, it's less than 7, it's acidic. Then the person calculates the pOH and go, cool, it's above 7, it's basic. And the same solution is acidic and basic at the same time. So don't do that. Yes. So it should only be 1. Look at the pH scale to determine that. I've never had anybody go for the trifecta of acidic, basic, and neutral at the same time. So just pick 1, look at the pH, and you'll probably be in good shape. Any questions on that there? All right. Let's do some practice here. Why not? We got this one here. Let us calculate a bunch of stuff here. We want to know, what is the H plus concentration? What is the OH minus concentration? What is the pOH? And is it acidic, basic, or neutral? And for the one on the bottom, let us do What is the H plus concentration? What is the pH? What is the pOH? And is it acidic, basic, or neutral? All right. So for each of those, with the information given, pretty much calculate everything. Make sure your calculator works, not broken. And there was. Let me fill some things in first. Sorry. There's actually a couple other things that will probably be helpful with that calculation I just gave you. So these are important, the pH and the pOH, and obviously this guy in our KW. But if we do have the pH value given to us, from the pH value, we can calculate. And the H plus concentration would be the inverse log of the minus pH. Now, on most people's calculators, when you hit the inverse log, that's going to be a 10 and a caret. And you do the negative of the pH. To do inverse log, it's like the shift button or second button on your calculator, usually on the left, and the log button. It might be how you're doing scientific notation incorrectly. If you want to calculate from the pOH, or if you're given the pOH, you could calculate the OH minus concentration. And that's basically the same calculation as the inverse log of the minus pOH. So the inverse log of the minus pOH. And again, on your calculator, that usually will pop up at 10 and a caret. Make sure it's negative pOH. So that's the way you can calculate the H plus concentration or the OH minus concentration if you're given either the pH or the pOH. Again, the inverse log, second log, or shift log on most calculators will do that for you. Sorry about that. I forgot to throw those in, I suppose. Any question on that there? All right, so now that we have all of them that we need, hopefully give that one a go that we were. Okay, let's take a look, see how we're doing. So starting with the first one here, we are given the pH, which is 4.82. So really at this point, you have a couple of options. You can calculate the pOH off the bat. You can also use the pH to figure out the H plus concentration. I'm going to go with the pOH first. So remember that the pH plus the pOH will equal 14. That means that the pOH would equal 14 minus my pH of 4.82. And that's going to give me, thank you, 9.18 it is. Again, at this point, you have a couple of options. Now that you have the pOH, you could also get the OH minus concentration from it. I'm going to use kind of the newer calculation we just talked about. So from the pH value here, I'm going to calculate the H plus concentration, which once again is the inverse log of the minus pH. And again, on most people's calculators, usually there's like a second button or shift button top left. There's usually a log button that says like 10 to the X, and that is basically the inverse log. It's basically how you do that. You hit that button, then you hit that button. And when you do it, you usually will pop up a 10 and a caret on most people's calculators when you actually do that. So punching that in correctly, it will give you a 10 and a caret most likely. Make sure you hit the negative button and know 4.82. And if you do that, we get negative 4.82. Looks like we will end up here with 1.5 times 10. That's the zeros. 1, 2, 3, 4, 5, minus 5, I think. It does need molarity at this point. Any question on that calculation? Again, if you have a non-display calculator, you would need to put in 4.82 first, hit the negative button, and then hit the second log button to do that calculation. Now, this actually opens up other possibilities at this point. Since I do have the H plus concentration, if I wanted to use the KW, I could. And like we did before, to calculate the OH minus, or again, I can do the same calculation with the pOH that I have. And I'm going to do that again. So the OH minus here will equal the inverse log of the minus POH. Once again, when you hit the shift or second button and log button, probably will pop up a 10 and a caret on your calculator, make it negative 9.18. And if you do that, maybe negative 9.18, going to give us a 6.6 times 10 to the minus 10, looks like, molar. Any question on that calculation? At this point, we do want to determine is it acidic, basic, or neutral, and which one is it? It is acidic, and it is acidic because we should look at the pH value here, which is less than 7. So we do know that it is acidic. Any questions on any one of those calculations? By the way, in terms of like sig figs, hopefully I did all right. Let's see. This number here, which is actually the pH type value, had 2 decimal places, which means this guy should have 2 significant figures, same there, and 2 decimal places there. So pretty good. Not too bad, I suppose. Any questions on any of that there? All right, looking at the bottom one here. Or not, hit the right button, try that, there you go. Looking at the bottom one, we are given the OH minus concentration. So once again, you can at this point, because they did give you the OH minus concentration, there is nothing wrong with using the KW expression like we did before. It works just as good in this case. So if we went that route, for example, we would then have the H plus concentration would equal 1 times 10 to the minus 14 divided by 2.5 times 10 to the minus 7, and 1 to the minus 14 divided by 2.5 to the minus 7, going to give us, looks like maybe 4 times 10 to the minus 8 molar. At this point, we have both the H plus concentration and the OH minus concentration, which means we could go right into our equations. pH would equal minus the log of the H plus, and that would then be minus the log of 4.0 times 10 to the minus 8. And looks like 7.40 on this one. Now, and once again, I do have the OH minus, which means if I wanted to, I could do the POH as minus the log of the OH minus. I could also, now that I have the pH, simply subtract 14 and get the POH the same way. So I'm just going to do that. pH is equal to 14 minus the pH. That would give us 14 minus 7.40. Going to give us a POH there of about 6.6, looks like here. This one would be slightly basic at 7.4. It's just slightly over 7. So it would be there. Question on any of those calculations there? So you do have a variety of ways you can kind of do some of these problems depending on, which sort of path you choose. Like I said earlier, they all should really get you to the same spot. You might have a slight difference if you did a lot of rounding or something like that, but really you should kind of end up with the same answer. Any questions on any of those there? All right, let's try one more here just to make sure calculator is still not broken. All right, so for this one, we're doing the same thing, pH, POH, OH minus, and we'll add, is it acidic, basic, or neutral to this, starting with an H plus concentration of 3.5 times 10 to the minus 6, looks like. So in this case, we got H plus given to us, which gives us really 2 options up front. We could get H, or we could use KW and get the OH minus. Again, neither one's a bad choice. I'm going to calculate the pH here. So the pH will equal minus the log of our H plus, and that's going to be minus the log of 3.5 to the minus 6. And that will get me 0.5 exponent minus 6. Looks like a 546, perhaps, there. Now, for me, I think the simplest thing to get to the POH would be just to take the 14 minus the pH. And in this case, that means we will do that move. And that gets us right to our POH of 854. And at this point, I'm going to take the POH value and use it to get the OH minus concentration by the inverse log of the minus POH. Again, usually we'll put a 10 and a caret. Make sure you do negative, not the subtract button. 8.54. And that will get us, where are we at there? Where's my kick button? There it is. Minus 8.54. And looks like maybe a 2.9 times 10 to the minus 9 molar. If you change it to scientific notation. If not, you probably got a bunch of zeros with a 2 at the end of your calculator where it ran out of room, and then you should hopefully be okay. I hope. Question on that there. This would be acidic, basic, or neutral. One should be acidic based off of the pH value. Question on that there. Yeah. So if you're given either really the pH or the POH is kind of the, I guess the best way to say it is it's kind of the reverse of this operation here. So you from the pH, it actually tells you what you can get from it. pH means you get the H plus concentration, and that's the way you would calculate this by taking the inverse log of the minus pH or negative pH. And the same thing with the POH. The POH tells you you can get the OH minus concentration directly from it. By doing the same calculation. So it's really kind of the reverse of the pH calculation mathematically. That's the inverse log of it. Other questions? Questions on how to calculate pH, POH, H plus, OH minus. You do need to know those formulas, and more importantly, you do need to know how to do them and punch them into your calculator. If you are still having trouble with your calculator, not sure where any of these buttons are, once again, come see me at some point with your calculator. We will find them together if you need. Any questions on any of that there? Yeah. All right, so let's talk a little bit about acid strength. So acids and bases, they are electrolytes, which means they basically will break apart into ions in solution. Strong acids are strong electrolytes, and strong bases as well are also strong electrolytes. Weak acids and weak bases are weak electrolytes. A reminder that if it is a strong electrolyte, when it's in solution, it will 100% dissociate or break apart into ions. You'll have none of the whole units still together. So for example, if you had your hydrochloric acid, which is a strong acid, it in solution is basically H plus and Cl minus. And in solution, that is pretty much 100% of what you have floating around in there. You have none of these units still left together. This is also why it is a strong acid, because it will produce a lot of H plus really quickly. And because it will produce a lot of H plus, the pH should go up or down. Should go down, right? The more H plus you have, the lower the pH will be, the more acidic it would be in that solution. Something like this, which is our friend, that is acetic acid, yeah, vinegar, basically, yeah. So that's acetic acid, which is a weak acid. We know that, by the way, because it's got the arrows heading in both directions. It's a weak electrolyte. So unlike hydrochloric acid, which is a strong electrolyte and a strong acid, in a weak acid, that is actually mainly what you have in solution. So you mainly have actually acetic acid still together, but it will produce a little of these ions or a few of these ions. And because it's still able to produce some free H plus in solution, it's still considered an acid, but it's obviously nowhere as strong as a strong acid would do. Strong acid pretty much goes for a swim, and you got a lot of H plus really quickly. A weak acid, it's got to set up an equilibrium and produce a little bit of H plus. You don't get as much kind of produced. What are some strong acids? Well, there's a nice little list right there. Some strong acids, by the way, are good to know. There is our friend, hydrochloric acid, our good pal, nitric acid, perchloric acid, a little HCl4, sulfuric acid, hydrobromic acid, hydroiodic acid. Those are like your 6 sort of strong acids. Those are something, you really should know. It'll make some of the calculations easier if you do come across one of those guys. So pretty much all those guys will, with sort of a little bit of an exception on sulfuric acid, but pretty much all of those guys will 100% break apart when they're in solution. So if we have something like this, 100% of them are going to send their H plus basically over, and we will get H3O plus and Cl minus. This guy will get H3O plus, sends H plus over, and nitrate. This guy is sending its H plus over. We'll get a little H3O plus and some perchlorate. And this guy's sending it over. We will get H3O plus and a little HSO4 minus. So in solution, pretty much 100% of what we have will be what's on this side. And again, we do produce, in this case, the H3O plus because we did include water in this dissociation reaction. You do not need to include water. You can, like I wrote above here, simply just write HCl breaks apart into H plus and Cl minus. So they're equivalent equations. They're both good. And again, most of the time, I probably will write acids like that without the water, just making H plus and simply like Cl minus. Any questions on that there? All right. Now some weak acids. Here are some weak acids. We got some hydrofluoric acid. We got nitrous acid, and we actually have water as well. So in this case, again, each of these guys are going to send their H plus over, basically. And again, here they did write the water there in the equation, so we'll finish it up correctly based on that. That will give us H3O plus and F minus. That'll give us H3O plus and NO2 minus. H3O plus and SO4 2 minus. And that will give us our H3O plus and our OH minus. Now, again, in this case, what you mainly have, it's actually everybody on this side in solution. So you mainly have those guys here on this side in solution. Just like the strong acid, you could write kind of a shorter version of this equation, the dissociation of a weak acid, kind of the same way as we did the other. You could write HF and just have the arrows where it breaks apart into H plus and F minus. So again, you can leave the water out of the dissociation equation, and you'll just end up with H plus on the other side rather than H3O plus. Any questions on that there? There's some strong bases, sodium hydroxide, potassium hydroxide, and barium hydroxide. Pretty much if you look at group 1 and 2 on the periodic table, somewhere right around sodium and potassium, you kind of come down, hang a right, and calcium and those guys. Any of those guys kind of with hydroxide, a lot of them are strong bases, which means they do 100% break apart in solution. They are strong electrolytes, so pretty much 100% of what you have going on is what's on the product side is everything that will be in solution. You'll have none of these guys still really there in solution. And that is again why they are considered a strong base, because as soon as they go for a swim, they will produce a lot of OH minus really quickly, which means the pH then should go up, right? More OH minus, less H plus, pH goes up in that case. And again, that's why they are considered strong bases, because they 100% dissociate. There are some weak bases that are much like weak acids. They will mainly stay together, but again, will produce a little bit of hydroxide in solution, which is why they are considered still bases. I think we have that on the next one here. So these are some weak bases like F minus. So in this case, the H plus is actually coming this way. Out of all the sort of reactions or equations, I would recommend putting water in a weak base equation, because it just helps you maybe visualize what is being produced and where the hydroxide comes from. I definitely put it into the weak base equation. So on that transfer there, we get HF, which by the way is where it comes from, right? And we do produce OH minus in that case as a result of the water giving up the H plus. Here we get HNO2 as that guy accepts it, and we make a little hydroxide here as well. Again, in solution, this is mainly what you have on this side, but it's still able to produce a little bit of hydroxide, so still considered a base. Clearly nowhere near what a strong base would do. Again, strong base just go for a swim. Now, there is an important sort of relationship between sort of acids and their conjugate pairs, which is really important for something we'll talk about a little bit later on this chapter, which are salts. The relationship is this: if you have a strong acid, its partner, which would be the conjugate base, is going to be relatively weak. So what does that mean? It means, as we will talk about later on in this chapter, it pretty much will not continue to react with anything. So it's just going to kind of hang out. It's going to be kind of neutral. Not much is going to go on with it. If you have a strong base, its conjugate partner, which would be the conjugate acid, will also be weak. Also, same sort of result there. It will pretty much just kind of hang out. It's not going to continue to react or anything like that. Now, if you have a weak acid, its conjugate partner, which is the conjugate base, will be relatively strong. And when we talk about it being relatively strong, we're not talking about it being really a strong base, but it will continue to react. And we'll talk about that a little bit later on. And that's an important relationship. And our weak base, its conjugate acid, will be relatively strong as well. So the relationship between the acid and its conjugate partner is basically an opposite relationship. If it's a strong acid or strong base, it will produce a conjugate partner that's considered to be relatively weak, which basically means it will not go on and react with water. It will not go through what's known as a hydrolysis reaction where water is involved. And if you have something that came from a weak acid or weak base, its conjugate partner on the other side actually will continue to react with water and will result in affecting the pH of the solution, which we will talk about. Any questions on that there? All right, here's a table. You have a similar one in your book of some of your strong acids and opposite sort of relationship. As the acid strength increases, the conjugate partner base is weak. stronger base, weaker acid. So again, that opposite relationship as one goes up and one goes down. And again, in solution here, we see a strong acid will 100% break apart, and 100% of what you have in solution is those guys, as opposed to our weak acid, where mainly that is what you got going on, and a few of those guys kind of hanging out. Any questions on that there? All right, we will lay it up there for today, I think.